Hi guys, how's it going? Terry Brown, Mechanical Engineering here with another engineering mechanics video. This time we're going to look at another simple rigid body equilibrium problem. All right, so let's have a look at the problem. Okay, so here we have the problem. It's just a simple beam-like structure or component built into a wall over here at the left at point O, and we've got a force here of 100 newtons acting at an angle indicated by our 3-4-5 ratio triangle as shown. And we're needing to solve for the unknown reactions at the supports. Well, there's only one in this case. And we're told to draw the free body diagram, which of course we shouldn't need to be told to do. You should know that that's how we solve equilibrium problems, by drawing our free body diagram first. So the first thing we do is to draw a simple outline of the shape that we're analysing, or the shape of the body or object that we're analysing. So we've done that here already. Put on our reference dimensions. So in a rigid body equilibrium problem, the dimensions are important because we need to calculate moments. So now we need to start putting on our forces and or moments that are acting on the body. So usually I start with the loads and then start thinking about what's happening at the supports. So we've got our applied load here of 100 newtons. Now over here at point O, our beam-like structure is built in. So my little device here, and we've got a force that's going to be down like this. So I've got to pull, I can't push. Well, I could push, and that's going to tend to rotate around point O. So if in thinking about our supports, so looking at the little video of me just off to the side of the solution, if you look in there, you can see what I'm showing, hopefully. When we draw our reactions at supports, we think about the motion that's either constrained or is free. So in this case, it's completely built in. So if I tighten this nut up really tight, so there's enough friction to stop it rotating, or if I put in two nuts here, then that can't rotate anymore. Okay, so at the moment it's free to rotate, but if I draw my free body diagram to match this is not free to rotate, so I need to put in a moment reaction here. Okay, on my model here, I can't pull it out to the right, and I can't pull it upwards. Okay, so there must be two forces there, right, or a single force in an unknown direction. Right? But usually we put on our unknown forces as two unknown components of a force. All right, so I've started here. So I put on a horizontal force reaction, and I've already put on the arrowhead. Remember that when you draw your free body diagram, all of your forces and moments must have arrowheads indicating their sense, because that's what tells you whether to put a plus or a minus sign in front of that term in your free body, in your equilibrium equation. In this problem, it's fairly easy. We've just got a horizontal component of this 100 Newton force acting to the right. So this force here will be acting to the left. Okay, so this will come out as a positive answer in our, if we get our algebra correct. The other thing we could have done is just put it acting to the right if we didn't know, and then when we do our equations of equilibrium and our algebra, it'll come out as a negative number. In labeling my unknown here, so some people you'll see will have just O subscript X. As I've explained in other videos, I prefer to use a capital R or a capital F just to indicate clearly and unambiguously that this is a force that I'm talking about. We've now got the vertical component of the reaction force at O acting upwards, right? Because we can see from over here that we got this force is acting vertically downwards, or the component of that force. And then we have a moment. So this force here, as if we again look at my little model in the picture of me off, or the little window of me off to the side, if I pull down in the same direction that force is pushing, you can see that will be a clockwise rotation of the body, or tend to be a clockwise rotation. So here we need a moment to be anti-clockwise. Okay. Again, if you've got lots of forces and other moments acting on this thing and you don't know, it doesn't matter. Just assume a sense for the unknown moment, and then your algebra and your final answer will tell you whether it should have been the other way or not. Okay, so we've now completed our free body diagram. We're assuming in this case that the weight of this component is negligible. for this problem. If it's not, then it's pretty easy just to add another force here. But I've kept it simple for this problem. All right, so just redrawing our free body diagram here on the next page. Again, you don't need to redraw it. I've just copied it over so I can refer to it as I'm explaining my solution. So I've started off with, in this case, a force equation. So in a lot of problems, we start off with the moment equilibrium equation because that enables us to find an unknown straight away that we couldn't find easily using any of the other equations. But in this case, we've only got one force, and so we can use the force equations directly. So we've gone some of the forces in the x direction equals 0. In this case, I'm not sure whether I put on an indication of the x and y coordinate system. So I've just put it here in my equation of equilibrium, clearly showing that horizontal and to the right is positive for x. Okay, so this is the fully correct written form of the equation of equilibrium. So let's look at our forces that we have. So we've got minus ROX, so that's acting to the left. So according to our assumed sign convention of being positive to the right, that's a negative unknown force. And then we have the horizontal component of this force here. So I've just used the 3, 4, 5 triangle ratio here. If we look at this force here, and if we draw a triangle around this force, if we say that this is, let's say this was 50 long, then the vertical side here will be 30 and the horizontal side here would be 40. But we've got a force of 100. So if it's 100 long, then the horizontal side here will be 80. So 4/5 times 100 is 80. And the vertical side will be 3/5 times 100, which will be 60. Yeah? So hopefully that makes sense. If you're not sure, and even just as an exercise, work out what this angle is. So use Pythagoras, work out what this angle is, and then do 100 times cos of that angle, right, to get this horizontal component here. All right, so ROX equals 80 newtons. So some of the forces in the y direction equals 0. So we've now got the vertical component here will be 3/5 times 100. And in the negative direction, and we've also got ROY shown in the positive upwards direction. Okay. So this shows you why it's important that on your unknowns you show the arrowheads, because without them you can't check these numbers or these signs out the front of your terms. All of your forces and moments on your free body diagrams must have the arrowheads so that you can correctly write the equations, and so if someone else or even yourself later on can come back and read them and properly interpret what you've done. Okay, so just rearrange that and we get ROY equals 60 newtons. Some of the moments about 0.0 here. So again, the fully correct way to write this equation, sum of capital sigma moments, capital M, anti-clockwise positive, indicate where you're taking moments about. Must have this subscript here, right? All equal to 0. So we've got a moment here, that's the reaction moment, and then we've got the moment generated by this force over here. So ROY and ROX both pass through 0, so, or 0, so they have no moment. So we now need to look at this force here. So we could try and work out the perpendicular distance from 0 to the line of action of this force, but since we've already worked out these horizontal and vertical components of this, and we've already got these distances, we can just go straight to Varanon's theorem or the principle of moments. So 4/5 times 100 is the horizontal component here, times perpendicular distance of 2. Right, so remember that the line of action will be horizontal along here, and the perpendicular distance to that line is 2. Is it clockwise or anti-clockwise? Let's have a quick look with our little model here. So it's there. We're looking at the horizontal component, and it's putting it this way. So that's rotating in a clockwise direction. So that's negative. So put the negative sign out the front. then we've got our vertical component, 3/5 times 100 times its perpendicular distance. So the vertical component is acting down here. Perpendicular distance is 5. So 3/5 times 100 times 5, is it clockwise or anti-clockwise? Let's have a look at our little model again. Pushing down here. Which way is that going? Going clockwise. Again, if you don't have a little model like that, you can, of course, just grab a pen and do the same thing. The horizontal one was a little bit difficult, or more difficult, but if you just need to remember, right, the line of action and the perpendicular distance, right? Not the point of application of the force. That's important. It's the line of action, right? So this one's negative also, all equal to 0. Rearrange that, put the numbers into your calculator and get 460 Newton meters for the moment reaction. Okay, in this one I haven't done any quick checks. I kind of done some checks as we worked through and thought about it. One thing you could do is to, instead of using the principle of moments here or Varanon's theorem, you could try and work out this perpendicular distance. So let's have a look at this. So that's 5. Yeah, so it's about 5, right? So here we got 5. So you can see it's not going to be 46, for example, or 4,600. Or 100 Newton meters. So our ballpark guesstimate here, right, if we drew this accurately and drew this line, right, that line from here to here, is something around about 5. So that tells us that we haven't made a silly mistake in here, for example, right? So we might have put a plus in here instead of a minus, and then we would have got a much smaller magnitude of our moment. And that would have told us, hang on a second, there's something not quite right going on here. Okay, so that's the end of the problem. Hopefully that was helpful. See you in the next video. Bye for now.